Perfect. There are a few things that we need to write because these words are not in the right places right now. We need to match the word with the correct definition. So let's do some of the ones that we know. Like, Andrew, what is one word that you might know up here? Got tangent, diameter, chord, secant, circle, radius. Radius. What is a radius? That's not a radius. It would be half of the distance across the circle, right? So it's probably going to be like the bottom one, the distance from the center to the edge of a circle. So what you want to do is write radius on that line right there. That is a radius. Now diameter is what you gave me a second ago. A diameter is the distance across the circle through its center. So that's where you're going to want to put diameter. Now, once you write it on the correct line, you can cross it out on the other side of the page so you know you've already used that one. What is some of the other ones we have? We have 4 left. Anybody know any of the other ones? Like a line that intersects a circle in 2 points. What? That is a secant. Yes, a secant is a line that intersects in 2 points. A line is telling us that it goes on past the circle. If it was a line segment, then it would end on the circle, but this is a line, so it goes past. What about the set of all points in a plane that are equidistant from a given point, called the center of the circle? So if I've got a point in the center, and I put a bunch of points that are all equidistant to that center point, what did I just make? A circle. So that's actually the technical definition for circle, is that it's the set of all points that are equidistant from a given point called the center. They're all the same distance away. That would be a radius distance away from the center point. Now we got 2 left. We got tangent, and we've got chord. A line that intersects the circle in exactly 1 point. Basically a line that just touches. What lines touch? Would not be a chord. Got to be tangent. Tangents touch. Tangents, all they do is they snuggle up next to the circle and they touch it in 1 spot, and that's it. That's what a tangent does. A chord is one that's a segment. A chord is got 2 endpoints that are on the circle. So in other words, a diameter is actually a chord. It just happens to go through the center, but it does touch and it has 2 endpoints on the circle. So those are the 6 words that you need to put in. Those are our 6 vocab terms. You can cross out the words on the side now because you don't need those anymore. You can write them on the line. All right, now I want to show you what some of those look like. So those were the technical definitions. Now let's go to what they look like. You have both of these pictures on your paper. My little magic revealer here, if I drag this over the circle, it tells me that that's a radius right there. So that line that's pointing down here from C to E is a radius. Okay, that line's a radius. What do you think from B to D? From B to D, this line across would be a diameter. This BD right here would be a diameter. That's pointing at this line right here. That's a BD. What about from L to M? It's got 2 endpoints on the circle. That would be a chord. Now notice the chord and the diameter are both in the same box there. Actually, both of those lines are chords. The diameter just happens to go through the center. But LM is a chord because it's ending on the circle, and BD is a chord because it's ending on the circle. But the chord that goes through the center is called the diameter. What about this bigger box or bigger circle right here? What is GK going to be? It goes through the circle and touches in 2 places. Tangents just kind of snuggle up and touch it once. It's going to be a secant. They call it a secant. So this over here was our radius, and this line here from G to K, since it goes past the circle, it doesn't stop on the circle, it's going to be a secant. It basically cuts through the circle. And then the last one at the bottom does kind of snuggle up to it right here, touch the circle, that point F, and that would be a tangent. It's just touching. Tangents, all they do is touch. Now I know the circles there are small, so you're probably just going to have to put arrows and write it around the outside of it. Try to save paper, so you've got plenty of room in the middle of your paper to write work, and at the top and on the sides you can do some work. So you got a room around it, so just kind of fill in the work around the pictures. Okay, circumference of a circle is the distance around it. You probably remember those things, but the distance around it is called the circumference. The formula for circumference is pi times diameter, or 2 times pi times radius. You could use either one. Because 2 radius, or 2 times radius, is the same thing as a diameter. If you take a 2 and you multiply it by a radius, one radius would be here and another radius would be here, so that whole 2 radius would make a diameter. So you could do 2 times radius or you could do diameter. It's the same formula. It just depends on what they give you in the problem. If they give you the diameter in the problem, then use the diameter. If they give you the radius, then use the 2 pi r. So it just depends. Area of a circle is the region enclosed by the circle. So it's the inside part. Just the same thing for area of any shape. The area for any shape is always going to be the inner part of that shape. So the area inside would be called the region inside would be called area. The formula for area is pi r squared. The way I remember it is we always measure area in square units. So you're going to use the formula that has r squared, because we need square units. The circumference does not use square units, so you don't need the square formula. You just use the 2 pi r formula. Area is always in square units. You need the r squared. Still here? Okay, a couple of practice ones. A couple of examples here. The trundle wheel makes 10 revolutions when Jamal measures the distance from one side of the street to the other. So he's got one of those measuring wheel things where they walk it across it. They use it when they measure big distances. You don't want to pull out a tape measure for a football field. It's too much. So you get one of these things, you walk along, it does the wheel, and it measures it as it goes. His wheel is a 2-foot diameter. So across his wheel is 2 feet. He's rolling the wheel, and it makes 10 rolls to get to the other side. So they want us to find out how wide is the street. Do I need area or circumference on this one? Not area. Circumference. Because we're talking about a revolution around the circle. So it's got to be circumference. So we're going to use C equals, and should I use pi times diameter or should I use 2 pi r? What did they give me in the problem? They gave me diameter. So I'm going to use pi times diameter. In this case, it's going to be pi times 2. And in my calculator, I'm going to get 6.28 when I multiply 2 times pi. I'm going to use decimals here. What does that 6.28 represent? 1 revolution around the circle, around the wheel. How many revolutions did it take to get across the street? 10, right? This represents 1 revolution. I want to multiply it by 10 revolutions. If I multiply it by 10, I'm going to move it over one place. So I'm going to get 62.8 feet is the width of street. The width of the street is 62.8 feet. Okay, if you want to move too, there's things around there. Yeah. Width of the street. Width of the street. Okay, now example 2 down here. The distance from the center of a bicycle wheel to the outer edge of the tire is 13.5 inches. What did they just give me? Distance from the center to the edge. Call the radius. And it's 13.5 inches. So from the center to the edge is a radius. That's 13.5 inches. How many times does the wheel turn? So again, we're talking about circumference. It's turning. So how many times does the wheel turn to go 400 feet? So we know circumference, and this time I'm going to use 2 times pi times radius, because they gave me radius in the problem. So it's going to be 2 times pi times 13.5. I'm going to get my calculator out, and I'm going to multiply those three together. 2 times pi times 13.5. You get 84.8. Circumference is 84.8 inches. 84.8 inches. Okay, think about 84.8 inches. We want to know how many of these circumferences would go into 400 feet. How many of those 84.8 inches would go into 400 feet? I've got inches and I've got feet. I need to convert one of them. Okay, let's take the inches and we'll divide it by 12. And that will give me how many feet that is. It's going to be 7.1 when you round it off. 7.1 feet. So how many 7.1 feet can go into 400? In other words, how many circles are we going to have around the outside of that wheel? How do I solve that? 400 divided by the 7.1. Put that in your calculator, you get like 56 point, how much? 3. 56.3 revolutions. And it's approximate. That's how many times the tire would go around in order for you to go 400 feet. You're going around 56.3 times. Okay, moving on to a few practice problems. We want to find the circumference and the area of these shapes. Circumference, area of these circles. So this first shape, what did they give me in the problem? Radius. So I'm going to use 2 pi r. 2 times pi times 8. I'm going to multiply those in my calculator. Basically, it's going to be 16 times pi, 50.27. And that would just be units. Area, what do I use for my area formula here? Pi times r squared. We're in area, we need square units. Pi r squared. So it's going to be pi times 8 squared. In other words, we're using 64 times pi, because 8 squared is 64. 64 pi is 201.06. 201.06 square units. Now you have room above it. You have some room in the middle or in the back or whatever. You can find room wherever you want to use the circumference and area of these. You might want to do the second one on top. Here, I'll do that too. Circumference, area. Okay, now how do I find the circumference of the second one? What did they give me this time? They gave me diameter. So instead of using 2 pi r like I did here, I'm just going to use pi times diameter. Pi times d, so it's really just going to be 14 times pi. Pi times 14, which in your calculator, 14 times pi, you get 43.98. And that's just units. Now be careful on the area. A lot of students get that picture, they do pi times 14 squared. That's not right. What would it be? 7 squared. Good. Pi r squared, not pi d squared. So it's going to be pi times 7 squared. So it's going to be 49 times pi. And you get 153.94. And that would be square units. Okay, circumference and area for the third one. Set up the circumference formula for me. What did they give me? Radius. So I'm going to use the same one I used before. I'm going to use 2 pi r, which is 2 times pi times 2.3. 2 times pi times 2.3 14.45 units. And then the area would be pi times r squared, pi times 2.3 squared. So 2.3 squared, and then we're going to times that by pi. We get 16.61, 16.62. So there's your circumference and area for those three circles. Okay, let's apply some of the formulas now. It says, what is the radius of a circle with an area of 907.46? Well, it says right here, what is the radius that we're looking for? And they gave us an area. So what formula do I have to use? I got to use my area formula, pi times r squared. Well, what are they asking me to solve for this time? The r, not the area. They gave me the area. So I'm going to take out the a, and I'm going to put in the 907.46. And I'm going to put equals pi r squared. I need to know what radius they use to get that 907.46. So how do I divide by pi, or 3.14. And so you're going to get r squared, and I'm going to round it to a whole number, is 289. It's like 288.86 or something like that. But you'll end up with a rounded off whole number of 289. How do I get r now? I don't want r squared. Just square root both sides. So my radius has to equal 17. So if you have a radius of 17, the area of your circle is going to be 907.46. So we just work backwards. Instead of multiplying pi times radius squared, we divided by pi and we square rooted both sides to get the r. What is the area? Again, we're looking for area. What is the area of a circle that has a circumference of 3 centimeters? Circumference formula, area formula. What do they have in common? They both have pi. They both have r. So if I find out what r is over here, can I plug it into this one? Yes. If I find the r here, I can plug it into the r over there. That's what I want to do. They told me that the c is 3. So I'm going to take out c and I'm going to put a 3. I want to get r by itself though. 3 equals 2 pi r. So what do I do to get r by itself? Divide by 2 pi. So r equals 3 divided by 2 times pi. 0.48. So the radius is 0.48. So my area would be equaling pi times 0.48 squared. Is there something I'm missing? Why's your foot on the desk? Like every time I turn around, you guys giggle. All right, we have pi times 4.8 squared. We found the radius to be, or 0.48, not 4.8, sorry. 0.48 squared. And then we multiply it by pi. You get 0.72 is your area. And that would be square centimeters. 0.72 square centimeters. Number, or the last one here, not the number. There's supposed to be a shaded part, and it didn't get shaded. So this is the part that's supposed to be shaded. If you want to shade that in, you could shade that in for a second, and that's the area that we're looking for. We're looking for that half a circle is actually what it is. And there was supposed to be a little right angle notation right there. So you've got a right triangle. The hypotenuse of the right triangle is the diameter of this circle, or a half a circle is what it is. We call it a semicircle. How can I find this diameter? Yeah, every right triangle, Pythagorean theorem works, SOHCAHTOA works, but in this case, Pythagorean theorem would work the best. 30 squared plus 40 squared equals c squared. I'm going to save you some time and tell you that c is going to equal 50. When you solve that, you're going to get a 50 meters. Now, that's not a whole circle. So if I used pi r squared, I would have too much. And I would just cut it in half, right? So I'm going to take my pi times my r squared, and I'm going to divide it by 2 to get my shaded part. Equals the shaded. What is my r, though? 25, not 50. R is 25, because it's only half of this diameter. So it's going to be pi times 25 squared, and then I'm going to divide it by 2, because I only want half the circle. I don't want the entire circle. So we're going to plug that into our calculator. We're going to get 25 squared is 625, times it by pi, and then divide it by 2. 981.75. So 981.75 square meters. Square meters. That's just the shaded part. So the shaded is that area right there. If you had not divided it by 2, you would have had a whole circle. That'd be over 19. That'd be like 1900 or something. All right, moving on to the next one. Got a couple of little application ones here. How do I find the area of the shaded part? What would be a plan? Not the work, but a plan. Find the area of a triangle. Find the area of a circle. And subtract the triangle out of the circle, right? Because we know the circle is bigger. So I'm going to take the circle and I'm going to subtract the equilateral triangle. How do I know it's an equilateral triangle? It tells me there's tick marks on all 3 sides, right? What do I know about all 3 angles in an equilateral triangle? All these angles are 60 degrees. Well, what happened down here? I cut it in half and I made 2 30s, didn't I? What if I was to bring a line straight down here? That's a special 30. Right here's 30. Here's 60. And you have your 90. That would be a 30, 60, 90. Now, it's going to come into play in a minute. We should be able to find the area of a circle pretty quick. Do we know the radius? 4. Radius, we're going to put right there on top of the radius is a 4. So it's just pi times 4 squared, 16 pi, which is 50.27. That's the area of the circle. 50.27. I need to subtract the equilateral triangle, which is base times height divided by 2, right? Do I know either the base or the height right now? No, I don't. But I do know I have a 30, 60, 90. I do know my hypotenuse is 4. Do you remember how to get from the hypotenuse back to the short leg? Just cut it in half. Hypotenuse cut it in half would be 2. That'd be my short leg. That's a 2 right there. You know how to get from the short leg down to the long leg? Multiply it by radical 3. So that's half of my base. So what's my whole base going to equal? 2 radical 3 plus another 2 radical 3. It's 4 radical 3. There's my base. So I'm going to put 4 radical 3 times the height, which I don't know yet, divided by 2. 4 radical 3 times what? What's the height? What would be the line that would go straight down through the center all the way to there? Remember, this piece was how much? This piece right here, 2. This radius was how much? 4. So this was 2, this radius was 4. Is this a radius? Is that a radius from the center to the edge? So how much does that have to be? The radius was how much? 4, so this radius is 4, and this was 2, so 4 plus 2. So this whole thing has to be 6. So your base is, your height is 6. So 4 radical 3 times 6, and then divided by 2 is going to give me the area of the triangle. 4 radical 3. We're going to multiply it by 6, and then we're going to divide by 2. Get 20.78. And you're going to take 50.27 and subtract 20.78, 29.49 square centimeters. 29.49 square centimeters. That would be your area for the shaded region, just the shaded part. Just the shaded part. So circle minus triangle will give you the shaded part. That's way up there. Okay, find the area of the shaded part. Before we do that, I need a volunteer for a little activity. That. Okay, how would I figure this out? What would be the plan first? Not the work, but the plan. Find the rectangle. Find the rectangle and subtract out 2 circles, right? So 2 of the circles. So find the area, subtract out 2 circles. I put a dot in the center because that shows that it's a circle, not just an O. So we're going to get the rectangle. So what would be my base and my height for this rectangle? What's the base? What would be the base all the way across? This is 8 right here. So guess what this is right here? 8, guess what that is? 8, guess what that is? 8 plus 8 plus 8 plus 8. 32, right? And then here I've got 8 plus another 8. That's 16. So 32 times 16 is going to be 512. That's going to be the area of the whole rectangle. Now I need the area of one circle, and then I can double it, because there's 2 of them. So it's going to be pi times the 8 squared, and then we're going to times it by 2. So let's go ahead and let me do that in my calculator. 8 squared is 64, so 64 pi, and then we times it by 2. Oops, I divided by 2, my bad. 64 pi times 2. And you get about 401.96, I believe. And if you subtract 512 minus 401.96, that's where you get the 110 point, that's actually 9.4. So this is like a 9.4. It rounds off to 110.1, which is what we got up here at the top. Okay, so there is the shaded region, shaded part. Okay, we're good to go? All right, next section, 8.6, is a really fast section. So this one we'll just breeze right through because we've already looked at similar figures. We know that similar doesn't mean identical. It means same angles but different sizes, right? The small and big one. So the scale factor of these two would be a 3 to 7 scale factor. Can I reduce 3 over 7? No, so that's it. It's reduced. So my scale factor would be a 3 to 7 or 3 over 7. Let's find the perimeter of these two. What's the perimeter of this first one? 3 plus 3 plus 3 plus 3, or 3 times 4? 12. And the perimeter of this one, 7 times 4? 28. So my perimeter ratio would be 12 to 28, or I could put 12 over 28. But we want to make sure we reduce ratios. So if I divided both of these by 4, then it's going to be a 3 over 7, which is exactly the same as the scale factor. So in other words, the perimeter ratio is the same as the side ratio because you're using sides to get the perimeter. So these two ratios are always going to equal. This one and this one will always equal each other. Let's look at the areas of these two squares. What's the area of the first square? 3 times 3 would give us 9, and the area of this one, 7 times 7, 49. So let's put that as our area ratio. 9 to 49, which would be 9 over 49. Another way to write that would be 3 squared over 7 squared, which tells me what do I do to my scale factor to get my area ratio. You just square them and you get your area ratio. You square here and you get your area ratio. Area is measured in square units. You're going to square them to get the area ratio. So if you look at this one down here, what's the scale factor of these two? Just A to B, or A over B. What's the perimeter ratio? A over B again, or A to B. Either one's fine. What's the area ratio? A squared to B squared. A squared over B squared would give you your area ratio. So perimeter and scale are the same. Area ratio is just squared. Okay, the ratio of corresponding sides of two similar. So it's the sides, and they're hexagons, and it's a ratio of 3 to 2. What's the ratio of their perimeters? Same thing, good. It's also 3 to 2. Or you could put 3 over 2, same thing. What would be the ratio of their areas? 9 to 4 is right. Because you would want 3 squared to 2 squared. You would want to square it, and that would get you your 9 to 4 ratio. The ratio of the lengths of corresponding sides of two similar polygons is 2 to 5. What is the ratio of their areas? 2 squared to 5 squared would be what? 4 to 25. Good. Find the ratio of their perimeters and areas. Perimeter ratio would be 5 to 7. Area ratio would be 25 to 49. You just square them. You square them both and you get your area ratio. That's how fast Section 8.6 is, and that's done. The ones on the worksheet tonight are pretty easy too, so I think you'll probably get those pretty fast. Okay, so there's 8.6. The last 4 slides are on 8.7, which is on probability. Geometric probability. Now, probability is right there, the desired outcome over the total possible outcomes. Like, for example, if I had a deck of cards here, and I said, if you pull out the ace of spades, you get $1 million. So I hold the deck out here, and all you gotta do is pull out the ace of spades. What's the chance that you pull out because you really want that ace of spades. You really love that $1 million. You got 1 out of 52. Is that a good chance? Not really a good chance. Now your chance of winning the lottery is even worse than that. But 1 out of 52, your desired outcome over the total possible outcomes. Now in geometry, the geometric probability is just the same, except you're using shapes, and you're using areas, and you're using lengths. So it's basically the same thing. You'd be like using the desired area over the total area. That would be the geometric probability. You take your desired area and you put it over your total area, or the desired length over the whole length. Like in this number line problem down here at the bottom, it says what is the probability that a point chosen at random on segment RS is on segment TU. The desired segment is between T to U. How long is T to U? It's 2. It's got from T or from 4 to or 5 to 6 is 1. So right here is 1 unit. Here's the second unit. So this is 2 units long. The desired is 2 units, and the total is 10 units. So your probability would be a 2 out of 10 chance, or when we reduce it, you'd get a 1 out of 5 chance. And you could actually also change that to a percent. It would be a 20% chance. 20% chance that a point would land between T and U on that line if you just threw a point at it. Or a random number generator randomly picked a point. Could be like a 5.3 or a 5.8 or 6.2 or something like that. Any of those points would be in between T and U. That's how long T to U is. So it'd be a 20% chance. It's the desired length over the total length. The desired length is in between those two units, and the whole total length is 10 units. Okay, another little activity. Bernice played the first one, so Bernice cannot do the second one. Sorry. How do I find the area of the red circle? Pi r squared would be pi times what squared? Pi times 3 squared. Okay, and then that's going to equal, let's see what we get on our calculator. 27 point something, I think, or 28 point something. 9 pi is 28.27. And we want to put that over the total area, which would be 16 times 16, which is 256. So 28.27 divided by 256, you get 0.1104. .1104, if you move this over two places, is 11.04%, or just 11.0%. And so that would be how we got 11% for that. Okay, moving on. 11% for that one. We good to go? Okay, one last little activity here. It's the desired part over the total part. The desired part is the shaded part. That's you do your square minus your circle. So it's going to be 144 minus, and the radius here is a 6. So minus pi times 6 squared, and that's going to be divided by 144. You do all this in your calculator, you're going to end up with 0.2146, which would round up to 21.5%. I'll assume that you can put this in your calculator. That'll be the easy part, because I need to get one last slide in. We got about 4 minutes. It's only one last problem at the bottom. So let's take a look at it. Here it is. Okay, an unskilled player tosses a dart at a board that is 4 by 4. 4 by 4. So I could put a 4 and a 4 here. What is the probability that it lands in the red region? Okay, so what's the desired? The desired is the triangle, right? The red triangle. And the total outcome is the square, right? So how do I get the red triangle? What's my area of that red triangle? Wouldn't it just be base times height divided by 2? Isn't it going to be 2 times 4 divided by 2? So that's going to be, how much is that going to be? 4, yeah. It's going to be area of 4. And then 4 times 4 is going to be 16. So 4 over 16 would be what percentage? That rounds to 1/4, right? So 1/4 would be 25%. 25% chance. Now I want to show you one last thing. Take a look at the line that I'm going to draw in right now. What do you see we have? We have one triangle here, another triangle here, another triangle here, another triangle here, and they're all the same size. So really you've got 1 out of 4 triangles, and the one triangle would be 25% because it's 1 out of 4.